they can watch it later, I suppose. There is a class right after here, so we can't really go over. So I'll begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students that are here, and also those who aren't here or just arriving. Pray that you'd help us to use this time wisely, Lord, to glorify you in what we do, Lord. In your name I pray. Amen. So, sorry to start without you. I guess there's, two more in transit. Okay, so let's get started here. So I want to talk about mixture problems a little bit. So sometimes I think when we get the book finally, I think he'll call this. Some people call this compartmental analysis. Is another kind of compartmental analysis. Another term that gets thrown at these sorts of things. But basically, the idea is pretty simple. You have something like a big tank, right? And to keep things simple to start with, we'll suppose that this has some, some fixed volume of water, all right? Of course, it doesn't have to be water. It could be something else, but fixed volume, right? And you also suppose that there's some kind of thing in it that mixes it, right? There's some sort of mixing, like maybe there's like a big, I don't know, maybe there's some giant with a big ladle and he's like stirring it. I don't know, whatever you want. Somehow it's being mixed, all right? Maybe there's a little fan in it that churns it. And then the idea is to study, you could, think about, so here I'm going to follow a specific example here. This is the book I had for my differential equations course when I was little. I actually was littler then, it's true. But anyway, this is, what is this? This is Introduction to Differential Equations with Boundary Value Problems by Stephen L. Campbell and Richard Haberman. Huh, that's the same Haberman. Anyway, so this, it's a nice little book. And this is a problem from it that I'm going to steal. So he has this mixing tank, fixed volume, 100 meters cubed, okay? Just to be specific. And the water contains a pollutant at a concentration of 0.6 grams per cubic meter. So here's the data we're given. Contains a pollutant at 0.6 grams per meter cubed, all right? That's initially, all right? Let's say that that's when t equals to 0. It has that concentration, all right? Amount per volume is called concentration, all right? And then it says cleaner water that only has a pollutant concentration of 0.15 grams per cubic meters pumped into this well-mixed tank at a rate of 5 cubic meters per second. So let me draw a picture of that. So you imagine, let's see here. I don't know, so maybe the pollutant we're talking about is mud, all right? So it's got like 0.6 grams of dirt per cubic meter, right? Then you've got less dirty water that you're pumping in here. It's got 0.15 grams per meter cubed, and it's flowing in here at what rate? We're given a flow rate there of 5 cubic meters per second. All right? So there's this water, 0.15 grams of pollutant per cubic meter, let's say dirt, and at 5 cubic meters per second it's flowing in, right? And what else here? Then water flows out of the tank through an overflow valve at the same rate as it's pumped in. All right? So then there's like this overflow. So here, overflow pipe. And since we said the volume is fixed, what does that mean? Right? So that means there has to be 5 cubic meters per second flowing out here, right? This water is neither created nor destroyed in this process, right? Okay, so there's a conservation of water. All right. But, you know, there's less dirty water flowing in. There's more dirty water there to start with, all right? So here's the questions that were asked. Determine the amount and concentration of the pollutant in the tank as a function of time. All right? So A, find the amount of dirt or pollutant, whatever you want to call it. You could make it Kool-Aid if you like, I don't know, whatever. In tank as function of time. And then B, a specific question. At what time will the concentration be 0.3 grams per cubic meter? All right. So this is a problem of differential equations. So the first thing you got to do is decide what it is that you're going to make the differential equation about. I mean, pretty obviously we're going to use time for the independent variable, right? That's kind of not up for grabs. But there's kind of two different things. You could either think about using the concentration. You could make a differential equation for the concentration, or you could make a differential equation for the total amount of pollutant in the tank at time t. Personally, I think it's way, way easier to think about the total amount of pollutant at time t, right? For example, you guys can tell me how much pollutant, how much dirt is there in the tank at time 0? Not 0.6, that's grams per cubic meter. So what's this say? Let's say Q is the dirt, all right? Let's say Y, we'll use Y, why not? What's Y of 0? Grams per cubic meter times what? What's the... Yeah, times 100 cubic meters. And so it's most natural in this problem to use grams. And so we get what? We get 60 grams at time 0. So that's our initial condition. So let's let y equal the number of y of t. So this is the problem statement, right? Everything after this is the solution, okay? So the rest of it's up to us. So first of all, we're going to let y of t equal the number of grams of pollutant, dirt if you like, time t. All right? And I think we're going to let t be in seconds, right? Why would I do that? Right. Exactly. Yes, Luke? By the way, am I bouncing?
Do we mean to have 3 grams per meter? Diluted solution is already 0.6.
Oh, yeah. There's a very important 0.3 in the book that yeah. I mean, that's still a reasonable question. The answer is never. But you don't need differential equations to figure that out. You just need some common reckoning, right? I think lots of people without much calculus background or even algebra background could tell you that, right? Very good. So let's fix that. Okay, so that's the start. We have to decide what it is we're trying to model. We're trying to model the number of grams of dirt in the tank at time t. So now that we've settled that, we try to write down our differential equation. So what's the differential equation? dy dt, right, equals what? Rate out? Excuse me, I can't do math. Rate in, right, minus the rate out. Or if you like, you could say rate in plus rate out, taking the rate out to be negative, right? So the rate being what? Number of grams per second, right? So we can't just, sort of a rookie mistake here would just to be put 0.15 for rate in, but it's not just 0.15. What is it? flow rate, right? So times 5 meters cubed per second. Now I'm writing the units here for a bit. When we do the math, I will drop the units, but it's good to do the units here to see that what we're doing is dimensionally consistent, right? So this thing is just 0.75, right? Grams per second. See how the meters squared cancel? If they, we might have to do a unit conversion in principle for an actual real world problem, right? Anyway, so you might be given it in terms of like liters or something instead of cubic meters or whatever. Rate out. What's the rate out? So the rate out should be the concentration, right? The grams per cubic meter of the water that's flowing out, and then times the rate out. Well, the rate out is also, the flow rate is 5 meters cubed per second, right? But what's the concentration of, I'll make it green, of this green water here? What's the concentration of this water? Yeah, it's a function of time, right? So if the well mixed tank, so to find the concentration, you take the total number of grams in the tank at time t, right, and divide by the total volume. That gives me grams per volume. So that's just y, which is, as you said, Luke, a variable, divided by what? Right, divided by 100 meters cubed. All right, so then that gives us what? Minus, let's see here. What's 5 over 100? 1 over 20 in decimal. 0.05. Okay, 0.05 y, and then technically times 1 over a second, right? I don't have to write grams there because there is a gram inside the y. Drives me nuts in physics when people write grams per second there. That would make it a gram squared per second in that term. There's a gram inside the y, right? Anyway, sorry. This is why I shouldn't teach physics. It makes me angry. Sorry. So anyway, so this, of course, is annoying. And so what differential equation do we want to solve? We want to solve dy dt equals to 0.75, all right, minus 0.05y in gram seconds, all right? And we just omit the units when we do the math because otherwise it just gets really cluttered. Okay? Okay, so then do the math. So we got dy dt plus 0.05y equals 0.75. What kind of differential equation is this? Right. It is exactly. It's a y prime plus py equals to q kind of. In other words, it's linear first order, right? So we use the integrating factor technique. What's the integrating factor here? Right? So it's kind of, the integrating factor here is kind of silly. It's just e to the 0.05t. So you multiply, and we get e to the 0.05t. I should confess, by the time we get to test 1, I think, you will already not do it this way. Like, there is a better way to do this that we are soon going to learn. But for the moment, we have to do it this way, okay? But it just so happens that there's actually an easier way to think about this. But, since time travel is generally frowned upon, we'll have to wait for that about a week. Anyway, so the point is that this, of course, is ddt of e to the 0.05t times y. And then we integrate, right? So if you allow me to skip a step here because I'm running out of board space, we get y of t is equal to like c e to the minus 0.05t plus, what's 0.75 divided by, let me write it down, 0.75 divided by 0.05 is 75 over 5, right? Also known as 15. So that's 15 e to the 0.05t. Oh, I'm an idiot. So sorry. When I integrate, right, what's the next step here? I didn't write it down yet. It'd be like e to the 0.05t y equals to 15 e to the 0.05t plus a constant, right? So when I solve for y, that exponential gets canceled out. There's just a 15 there, right? It's kind of a concerning noise. It's like the biologist let some bug out of their cages or something. I don't know.
I think just one of the doors just has alarms on it.
Ah.
Like when I took them, yeah.
Ah, I see. This door shuts too tightly. That will stop working soon. I could be wrong. I don't know. Maybe I'm wrong. Okay, so then what? We can figure out C. How do we do that?
T equals 0.
Right, so yeah, t equals 0. We know y of 0 is equal to c plus 15, right? But it's also equal to 60. So therefore, c is equal to 45, and we get y of t is equal to 45 e to the minus 0.05t plus 15, and of course that's in grams and seconds, and there it is. There's the amount of dirt in the tank as a function of time. So does this make sense? Like, is this physically reasonable? What happens as time goes to infinity? The solution goes to what? What's the so-called steady state solution here? Right, so we go to 15. That's basically what you might call y of infinity, right? Does that make sense? If you look at this, basically it should be like the water's all like the incoming water, right? And if you take 0.15 times 100 cubic meters, you get 15 grams. Makes perfect sense, right? It's going to be as dirty as the input water after a long time. Garbage in, garbage out, and thus it's always garbage in. And then just, I don't know, there's some stupid saying to say here. At what time is the concentration 0.3 grams per cubic meter? How would you figure out B there? I'm going to do it over here. Since we already know what I have down here. I can safely erase that, I think. A little bit tricky, right? What does it take to achieve that concentration? You need 0.3 equals to y, right, of the time we don't know, divided by what? The 100, right? Because it's always, to get concentration, take the grams, total grams, divided by the volume. So that would be the concentration. So that shows me what I'm trying to find. What I'm trying to find is what time gives us y of t equals to 30, right? So once you figure that out, then it's just algebra, right? Because then I've just got to solve 30 is equal to 45 e to the 0.05t minus 0.05t plus 15. So that gives me 15 equals to 45 e to the minus 0.05t. Divide by 15, I get 1/3 is equal to e to the minus 0.05t. Take the log of both sides. We get, log of 1/3, which is, by the way, minus the natural log of 3, right? And that's equal to minus 0.05t. So there you go, solve for t. You got the natural log of 3 divided by 0.05. That's the time in seconds when you'll get 30 grams and consequently a concentration of 0.3 grams per cubic meter. if I do the math, that works out to 21.97 seconds approximately. Okay. Any questions about this? All right, so I wanted to work this one out kind of slowly from start to end to give you the ideas. Now what I want to do is I want to take this example and I want to just twist it a couple different ways and show you how it changes the differential equation, but I don't want to solve the differential equation in each one of these twists because otherwise that would take too much time. And mostly you guys have, I think once you set up the differential equation, you're like, oh, okay, well I know what to do here, right? This is a known problem. Hopefully by now you're comfortable with this, right? Or you're working on that. There's still time, right? So let's see here. You guys, tell me some other ways we could, I'm sorry, I'm erasing, is it okay? So, some other ways we could twist this problem. Any ideas? Yeah, variable flow rate. Yeah, do that. So I'm going to continue to let y denote the number of grams of dirt in the thing, or Kool-Aid, whatever you want. Salt, usually people do salt. And then it's called a brine, right? Water with salt mixed in, it's a brine, like you might put on the roads for ice. I guess the first thing I could think about would be get rid of the overflow pipe, right? And then if you just let in, whatever, 0.5, grams per cubic meter at 10 meters cubed per second, then in this situation, you'd have dy dt, right, equals to 0.5 grams per cubic meter times 10 meters cubed per second, right? So that would be 5 grams per second. Yeah.
You wouldn't really need differential equations to solve it now.
That is true. I think this one you could just kind of write. Well, yeah. I mean, I guess fair enough, Luke. I mean, I guess I can do the calculus here without like breaking a sweat. Change in y is equal to 5 times the change in d, right? So yeah, that's kind of how that goes. Right. Exactly. Now, what if though, let's make it much harder. What if, on the other hand, we had an overflow valve, right? But it's a little bit narrower, and out here we only get 5 meters cubed per second. The fixed initial value, it's not fixed anymore. Let's suppose the initial volume is 100 cubic meters, right? And suppose it's of pure water. Right? So basically this problem, I mean, are you guys up to the previous stupid case? Can I erase this? Okay. So again, it's always rate out, rate in minus rate out if we take both as positive, And so the rate in is still what we just did. It's still 5, But what about the rate out? See, what I need, right, is I need the concentration, right, times the volume at time t, right? So the concentration, so here's a kind of model of it, that would be y over the volume, right, at time t, right? I'm sorry, I'm an idiot. Not volume, what do you multiply by? Concentration is like grams per cubic meter. We need flow rate here, right? Luke had suggested we can make a variable flow rate. I'm not going to go, I mean, you could do that also. But if the flow rate's just 5, at least I can just write a 5 here, right? But then, you see, I have to find out what's the volume as a function of time. How do you do that? We have to do some thinking, right? So if you look at it, the volume's linearly increasing, right? 10 cubic meters per second. Wait a minute, no. What's the volume?
I'm just adding 5 cubic meters per second, right?
Right. So it starts out at 100, right? And then, like you said, we're adding 5, so 10 minus 5. So we're in seconds, right? So I write 5t here. Does that make sense? T equals 1, 105 cubic meters. T equals 2, 110 cubic meters, and so forth. And so this actually is 5 plus 5y divided by 100 plus 5t. And for what it's worth, I think we could still solve this, right? I don't want to, but I mean, I think we might be able to, right? Because this is 5 over 100 plus 5t. There's actually hope of solving this without too much trouble, but I'm not going to do it. But you could probably do it. See, because it's still a linear first-order differential equation. It's just now the p is a little bit ugly. Yeah.
Why did it switch to positive?
Fall man. Let's see here. Yeah, my mistake. There you go. So do you think you can try some of these if I assign you one homework? I mean, I assigned you one homework, so hopefully you can figure it out. But
Speaking of the homework, you said if we reminded you to do something.
Yes, that is wise. So let me get out your homework and see if we can talk about them. If I can figure this out again. So I mentioned to those here, come on, let me go back to the... Come on, wake up. Apparently I have to wake up the computer before I press this button. Now some of these, like the first one's orthogonal trajectories. I think you guys should be able to make sense of that on the basis of, what's in the notes and what we did last time, right? So I won't say too much about that, right? So, but I will say this much. There's a k here. You need to somehow get rid of that, right, to find the differential equation. You need to find a differential equation which doesn't have a k in it as to capture what this family of curve looks like, right? So how can you do that? Basically just differentiate this, right? And then if there's a k left in your derivative, solve this for k and get rid of it. This means that k is equal to y squared over x, right? So you can get rid of k by just solving this for k. After you differentiate, you can, get rid of the k, is my point, right? Okay? Sorry. Here, number 2, you're supposed to find the velocity of a mass m, which is launched vertically with velocity v naught from a planet with mass m and radius r. Call the gravitational force is given by this. Assume the motion's directly vertical and y is the altitude of m. You may find the velocity as a function of y. Let me restate that. Find the velocity as a function of y. So maybe you guys, let's see here, maybe we can walk through how to set this thing up. So we're on this planet, right? Its radius is r. We got a mass up here, m. Is it m? Yeah, little m. Mass of the planet's big M, right? Force of gravity is like this, right? Now, is there any other force on the mass? No. I mean, it's just this gravitational problem, right? So that's the net force. So we set that equal to what? ma, right? Little m, because we're talking about the forces on the mass, not the forces on the planet, right? And so little m is what? M dv dt, right? Where v is what? dy dt in this case. Again, y is the altitude. So in the picture, y is this thing right here, right? Whereas this is r, right? Okay, so I said, what did I say here? Find the velocity as a function of y. Now, if I just solve that differential equation, well, that'd be pretty tough, wouldn't it? Because I've got a y, and I've got a t, and I got a v, right? So, I mean, there's two different ways you can go here. The one, of course, is you could say, well, that's also equal to what? This is the way I don't want you to do it. D squared y dt squared, right? So this is a second order differential equation in y. Second order nonlinear. We haven't really talked about that. But the cool thing is, right, we can use that this is m, and this is true because the motion's one-dimensional. The chain rule applies here. We've got dy dt, dv dy, right? Because the motion's vertical, I can reparameterize the velocity in terms of the vertical position just as well as I can parameterize it in terms of time. And so what this gives us is m v dv dy. But look at that. See, that brings us to the differential equation you need to solve, which is what? Minus g big M divided by r plus y quantity squared equals to v dv dy. I canceled out the little m because we're assuming it's non-zero. So you just got to solve this thing. Where what? Big G, M, and R are constants, right? Does that make sense? So I just want to walk through that with you guys. I know that you might be a little bit rusty on physics at this point, right? Possibly. So you'd like to also use your answer should include the V naught, right? See here. It's launched vertically with velocity v naught from a planet. So I think I'm assuming that, you can assume that y, that it's like here. Let's say it's launched with y naught equals to 0 and v naught greater than 0, all right, at t equals to 0. Hey, stop that. I guess if I actually plugged in my laptop, this would stop happening to us. Fine. Ever since Matthew, my 3-year-old, dropped my laptop a couple of weeks ago, my power cord hasn't really fit. So it's like, it doesn't, not that it doesn't work, obviously, because I'm still using my computer, but it doesn't really stay plugged in, so it's... I try anyway. All right, so next problem. Suppose a rocket car has an initial speed of v naught as it hurtles across a speedway. Sorry, this is my. I need to make sure I spend about a half-hour class on something beyond the application, so I'm be careful not to go too slow here. How much time do we have left? 12:30. Okay, we should be fine for about 15 more minutes of this. I do want to help you guys with these. So you have a rocket car with an initial speed of v naught as it hurtles across a speedway in a remote desert. Driver opens parachute, develops a retarding force. Oh, I'm sorry, a slowing force. Proportional to the cube of the velocity. Force of friction is minus kv cubed. Find the velocity. I forgot to warn you, this is not a safe space. I make a number of micro and also sometimes medium-sized digressions in this course. But, yes. Oh, well. Anyway, so find the velocity as function of time, find the function of position. So this is almost the same as this. You just have to do what? So we're not told otherwise, right? So the rocket's done, right? The rocket has, you know how rocket cars work, right? They go whoosh, and then they open the parachute. So we're after the whoosh part. It's got its initial velocity. It's just coasting, modulo the friction force, right? So anyway, you get the idea. Parachute. I can't draw a parachute. Whatever. Excuse me. So you got ma is equal to the net force, right? So here we've got m dx m dv dt. What's the net force? It's the force of friction, which is what? Minus kv cubed, right? So that you solve this for part A, right? Solve it. Your answer should involve v naught, right? At time 0, we have velocity v naught, right? And then for part B, you're supposed to what? Find the velocity as a function of x, right? So at t equals 0, we have x equals to x naught, and v equals to v naught, okay? So anyway, so same trick as before. This is m dv dv dx, right? By the thing I just did, I mean, fine, I'll do it within dx dt, right? So you got m v dv dx equals minus kv cubed, and you can solve that. That's how to get part B. Okay. I probably shouldn't have helped you with this one. Sorry about that. A tank initially contains 100 gallons of water with 10 pounds of lemon drink mix. Then at t equals 0, fresh water is added to the tank at 3 gallons per minute. And at the same time, 3 gallons are drained per minute from the tank. Assuming the tank is well mixed during this process, find the pounds of lemon drink mix as a function of time. If you like to drink your drink with a concentration of 1 pound per 20 gallons, at what time should you drink from the drain? Okay. It's a slightly non-standard mixing tank problem. That's pretty much the one I solved today. All right. Sorry not to make it more exciting. A chain is coiled on the ground. One end is lifted with constant force. Find the velocity. Suppose an RL circuit has a voltage source which varies with time according to E of t, V naught cosine t. Find the current as a function of time with initial current I naught. This is like an example in the notes. We just have to replace the constant E with the sinusoidal voltage that. Let's see if we can do that right quick. Which example in the notes am I talking about? Is an RL circuit, right? I guess I could search, but that seems like that'd be too easy. There's an E, there's an R, there's an L. We have a winner. All right, here it is. So you can also think of these as compartmental analysis, or you can think about the sum of the voltages around the loop is 0. But basically, Kirchhoff's voltage law says if you've got this circuit, right? So this is a resistor, this is an inductor, this is the voltage source. Kirchhoff's voltage law tells us that we have to solve E minus IR. I keep forgetting signs. Minus L di dt equals to 0. All right. So don't be scared if you're not comfortable with circuits and stuff. It doesn't really matter. It's a differential equation. This is the differential equation you got to solve. So to solve that homework problem, all you got to do is, instead of like this one thinks of this as being a constant, in the homework problem this is what? V naught cosine of something, I guess, or whatever, right? So you just put that here and solve the differential equation. Here the R and the L are constants, so you can solve it. Now is a good time to look at the excuse me. Sorry, I'm having trouble here. So let's just look over this problem for a second before we try to set up the lifting problem, okay? So a flexible rope, length 4 foot, 3 foot coiled on the edge of a balcony, 1 foot hangs over the edge. T equals 0, the rope begins to uncoil further. Find the velocity of the rope as it falls. How long does it take for the rope to fall completely off the balcony? This is kind of the same problem as your homework, but it's not literally the same, but it involves the same can of worms, let's say. It's a variable mass problem. So, I mean, the key here is you look at ddt of mv equal to the net force. External force, all right? And the net external force is just mg in this case. Now once I write that, that means I've just taken down to be positive, right? So that's a choice. Now, so for this problem, you've got this coil of rope, right? And so the other thing that you do is you let this distance be, what did I call it, y? Let me put my glasses on. Oh man, my glasses are back in my office. It's x. Okay, so I'm calling that x, right? So it kind of makes sense. X is increasing in the downward direction, so taking down is positive is also kind of natural here. But if the x is the length of the rope hanging over, that's the part that's we're treating as a point mass. So if you treat this as a point mass, the theory of physics says it's really at the halfway point, right? Not that really matters here because gravity is constant over the length. If it was a really long rope, really long rope, then you'd have to think about that more. But anyway, basically m is simply equal to lambda times x, where lambda is equal to the mass per length, right? So that's the idea here. And so we really have ddt of lambda x xv is equal to mg, but m is what? M is lambda x, right? G. So that's what Newton's law looks like for this problem. But then you do the product. I mean, why is this, by the way, guys? I don't know if you remember or not, but a more fundamental way to look at Newton's law is that the time rate change of momentum is the net force. So P is mv. It's only a special case when the mass is not constant that we get ma. Variable mass problems, you have to think about dp dt. Well, that's one philosophy. There are various philosophies about this. But anyway, product rule, what do we get? Lambda's a constant here, because we assume that the chain is like homogeneous, right? It's not like a really thick chain on one side and a really skinny chain on the other side. That would be worse. So then this is lambda dx dt, v plus lambda x dv dt, right? Equal to lambda xg. You notice by now there's a lambda, lambda, lambda. Get rid of them. And so this is really v squared plus x dv dt is equal to xg. Right? See? V squared plus xv dv, oh, what? I got a dv dt. So what do? I do the usual trick. I trade this for a v dv dx, right? And then I solve. Okay, past that, it's differential equations. It's just solving. The details are right there. Let's think about your homework problem. Because I think that's by far the hardest problem on your homework. All right? A chain is coiled on the ground. One end is lifted with constant force, right? Can I erase this? I don't want to erase all of it, but okay, so here's the ground, chain or rope, whatever, and then it's being lifted like this, right? And somebody's lifting it with a constant force, right? We call F naught, is it? Oh, well, you're not told, but let's call it F naught, all right? For the sake of the grader, let us call it F naught. This is a given but arbitrary constant. Find the velocity. So we're also going to assume that this chain is homogeneous, okay? We're going to assume that this has lambda as the mass per unit length, okay? So your solution's also going to have an unknown lambda, the mass density of the chain. Right? I mean, real world problems are like this. You have to invent variables to describe the problem, right? Your boss is not going to come to you and say, all right, I want a solution in terms of lambda f naught. I mean, he might give you the problem like that, right? It's up to you to invent the necessary labels for things in certain contexts. I mean, other times your boss is going to tell you to go get him coffee or whatever, but, you know. All right, so the chain is coiled on the ground, one end lift. Okay, so I suggest that in this situation, the natural thing to do is call the length of the lifted thing x again, right? But now I got to be careful because, or do I have to be careful? I don't know. I'm trying to think here. So, I mean, technically I should think about the center of mass of the chain and think of the whole thing as a particle as it's rising, you know? But since the force of gravity is constant along it, I can just as well think of the forces being attached to the end. I mean, it doesn't make any difference whether I think of the free body diagram in the center of mass of the system or not. But I mean, I'll do it over here, just for, think of this as being the center of mass. So we've got the F naught up, right? And then you've got the force of gravity this way, right? So let's see here. Here we go. We got ddt of mv, right, equals to what? Looks like I have to do minus mg now, right? Because of the meaning of x versus the last problem. The directions are opposite, right? So minus mg plus f naught, right? And then what do? I don't want to spoil the fun for you, but then you set m equal to lambda x and do much like the, much like the example we just saw in the books. But I think that's the starting point, right? That would be sort of the variable mass Newton's law to start with. So I did the physics for you. I hope you're happy. If you don't mind, I'm going to take a second to check the solution to make sure I have not misled you. Go away, go away. Yes, I'm sure. Oh man, I was about to ask you guys if you had any questions about the solution to last week's homework, but I guess we're a little bit short on time. I should probably not do that. You can, of course, send me emails if you have questions about it or anything like that. I have posted it. The solution to the problem you asked me about after class, Luke, it's there. If you look at the solution, you'll be like, oh, yeah. The thing I wasn't doing was, if you take a partial derivative with respect to y, stuff pops out of that. And then you just set y equal to 0 after you do that. Then you got a differential equation in x, which gives you an exponential. I just didn't, when I was talking to you after class, think to differentiate with respect to y. So.
How is it that we lost the function of x equals 4 solution?
Oh no, that's legit.
That is legit.
Yeah. I mean, your logic that there is also the identically one solution, I believe that's also true. I don't think that's wrong. Come on, I can't find the solution. Ah! All right. Come on. Where are you, Mr. Chain? Yeah. Tell you what. Want to know what the answer is? Want to know the answer you're trying to find for this one? You feel kind of torn about it, right? I mean, not really. So I derive the square root of f naught over lambda minus 2/3 gx. I do believe that assumes that we're starting with 0 chain and lifting with the chain being at rest, right? I mean, so the sort of natural initial conditions you might imagine. And what am I looking at there? I'm looking at v. The velocity as a function of x is this. So there's about a page of calculus between that and this, though. Yes, yeah, I mean, it's not, it's not like other, I'm sorry, you're tempting me to talk about various majors that I have less respect for, so I should not take the bait. Let's see here. Anyway.
Turn off the audio.
Turn off the audio. No, I should shut up. All right, so, yes, sir.
Could you explain real fast where you're talking about where the row, like when would it be important to count the chain as particle, like in the middle of
Sure. For example, if you're calculating the gravitational attraction between this rod and this, so I mean the point is, if the force of gravity here and the force of gravity here from this mass, right? If they're different, then oh, see, that's still not quite the right thing to say. How to say this? I don't know. I'm not thinking of the right example for you at the moment. The point is, when we have an extended body, right? Technically speaking, the particle model says you can think of it as if the extended object has total mass m, you can conceptually think of that as a single particle of mass m, right? At the center of mass of the object. And that's good, at least in as much as external forces are concerned. Like,
so in this example, since the differences are negligible, is that why we can?
well,
It didn't really matter on.
it doesn't. I mean, yeah, it doesn't really matter if I think about F naught applied here or I mean, it is applied here. So I mean, the other rule is, if I've got this force and this force, then you just think of them all applied at the center of mass, in physics. So I'm saying whether or not I think of the, actual pulling on the top of the chain, or if I think about the concept that this length of chain is like a particle in its middle, the center of mass, and then I think about all the forces being applied there, it's not the same math. I mean, I don't know. Sorry, I'm not thinking, I should be able to think of a good example where it matters. I mean, the place this comes up most and really will get students is when you think about like a ruler with a bolt or something. And so to illustrate that, and this you could of course actually do experiments on, but if you have something like this, right, and you just let it drop like that, you have to think about the force of gravity. Where's the force of gravity? Where do you think about applying the force of gravity? You think about applying the force of gravity to the center of mass of the ruler or the marker system here. And so that's where the force is applied, and that's where you think about like torque and everything else. Like the torque is given by r over half the length, and the force of gravity on the whole thing there, that gives me the torque, and I can calculate the angular rate of change according to the rotational Newton second law and stuff like that. But so that's going to come up here, but that would be. And I guess I could start thinking about differential equations problems that will be twists on this, but I don't. So. I think that students have plenty of difficulty just assimilating the mathematics in this course. I don't need to go too far in the direction of physics in here. We just I want to show you that you can solve problems with variable mass, with friction, interesting stuff, variable volume, mixing tank problems even. But it's not a physics course, so I try not to get too carried away. All right, so that's more or less what I have to say about applications in here. You're, of course, welcome to ask me questions in future classes, but I have assigned you homework that's due next Tuesday. And the last problem is about a little bit of complex variables stuff. So I want to just try to give you a quick introduction to what is a complex number and just a little bit about how we work with them. So here it is. Complex number system, C, is set A plus IB such that A and B are real numbers and I squared is -1. And I would say beyond that,